Just to recall briefly what we discussed last time was some elements of set theory and basic operations with sets, which you're probably very familiar with, and laws of such operations. Then we were talking about mappings from one set to the other. What does it mean that two sets have the same cardinality? And we probably ended up with discussing binomial coefficients and even Stirling numbers. Both of them satisfy very nice simple recurrence relations, and they're very basic counting quantities appearing throughout the whole area combinatorics. And combinatorics is the art of counting different combinations of interesting objects, finitely many. Okay, so let me start sharing my screen, and today we'll be talking about inclusion and exclusion formulas. Yeah. Okay, come on. Good. Okay. To start, let me discuss some motivation and explanation of what our first theorem in this lecture will be describing. So motivation would be, let's see, yeah, motivating examples for exclusion-inclusion theory or formulas. Say we have our global finite set in which our subset will be residing. And we say have, in the simplest case, a couple of subsets A and B with non-empty intersection. And we're interested to count the number of elements in this area I'm shading now. So count elements in, say, if this bigger sets, if those guys will be denoted A and B, and this total thing would be denoted by maybe N, universe U, and all of them are finite sets. So we want to count number of elements in U minus the union of A and B. How do we do that? Well, and say a more complicated example would be if we have three sets, say this is our U, the total set, and we say have A and B and C all overlapping with each other. So we have U, A, B, C, and we want to count elements in U minus A union with B, union with C. So let's solve the first simple case by hands, and we can work on some specific example a little bit later. So then the number of elements, so answer in the first case obviously would be take the number, so the number of elements would be denoted by this vertical no brackets, and this is, we should take the number of elements in U. Now subtract the number of elements in A and subtract the number of elements in B. This is not exactly what we want, because now we have subtracted the intersection twice, because those elements which lie both in A and B have been subtracted twice. So we have to put the number of elements in the intersection back. And this would be a correct formula. So if we want to treat the second case, we will have to do one further step. So case one, so this is case one. Now, if we want to treat case two, we're trying to do the following. They are the same thing. So we want to count the number of elements in the complement to the union of U and B and C. And so we start with U, the number of elements in U. We subtract A, we subtract B, we subtract C. But then we have done too much, yes? So we have subtracted pairwise intersections twice. So we have to put them back. So we have to put back A intersected with B plus B, A intersected with C plus B intersected with C. But then we put back too much because their common intersection, this thing, little thing, we have put back too many times. So we have to subtract finally the number of elements in the triple intersection. And that's kind of a situation we want to generalize. And instead of just 2 and 3 sets, we want to have a general formula. So if we have n different subsets, which might intersect in some arbitrary way, so what is it we should do to count the number of elements in the complement to the whole thing? Okay, so let me take some concrete example. So say in a class with 100 students, so we have 35 take class in combinatorics, and say 30 take a class in algebra, and say 9 take both. And we're asking how many do not take either algebra or combinatorics. Okay, so and the answer in this case, as we did earlier, we should take the total number 100, subtract 35, subtract 30, but then put back 9. And the total answer would be, if I'm not mistaken, 44. So 44 students take neither algebra nor combinatorics in this situation. Okay, now let me formulate the general theorem. So to do this, I need to introduce a certain notation. So we're given a set S, and some conditions, and conditions S1 through Sn, C1, sorry, C1, C2 through Cn, they define subsets in our S. So a condition is, for example, to take such class or take another class. Now, I will denote by capital N of C, say, CE1, CEK. This would be all elements small s in our set S, such that S satisfies condition C1, C2, and so on, C, I, K. Okay. So this symbol will denote a negation of Ci. So that means that the element does not satisfy Ci. Okay, good. Now the question we'll be asking, or the theorem I'll be formulating in this notation would be our first theorem today. It's theorem 8.1 in the book. And it says the following. So let S be a finite set of cardinality, or the number of elements would be capital N. And C1 through Cn would be some conditions on S. Then I want to count how many elements in my set S do not satisfy either of these conditions. So they violate C1, C2, C, and so on, Cn. So they are not in the subsets defined, in the union of the subsets defined by this condition. So in other words, this would be capital N of the negation of C1, negation of C2, and so on, negation of Cn. So we're looking at those elements which violate C1, C2, C3, and so on, Cn. And the claim is as follows. So this would be the alternating sum, so over the subsets I1, I2, and so on, Ik. So we'll be taking, so the total number of these guys is K, so this would be minus 1 power K, and we should take N of Ci1 and so on, Cik. I hope I put it correctly. We'll check. So in other words, what I'm saying is, so example would be what we had before. So N, say if we have three conditions, so we have C1, C2, C3. So then I'm saying that the number of elements which is in the complement to all these three conditions is N minus N of C1 minus N of C2 minus N of C3, which is this formula with exactly one element. Then it will be plus N of C1, C2 plus N of C1, C3 plus N of C2, C3, and finally minus again N of C1, C2, C3. Okay, yeah. So how do we prove this? Okay, proof. So in proof, we will see which contribution to the left-hand side of this formula. So say this would be my fundamental formula star. And to prove that it's correct, I'll check what contribution to the left-hand side and to the right-hand side is made by an element in our set. So let's assume that we're picking an element which violates all the properties, C1, C2, C3, and so on, Cn. Then it contributes 1 to the left-hand side because it's in the set which we're counting. Now let's look at what it contributes to the right-hand side. Well, it lies in the whole ambient set, yes. So it contributes 1 to this guy. But since it's violating all the properties, it contributes 0 here, 0 here, 0 here, 0 here, 0 here, 0 here, 0 here. So it contributes 1 to the left-hand side and 1 to the right-hand side. Okay, good. Now, I'll be picking an element which lies in the union, but we'll do it a little bit, we'll need some more information. So I'll be trying to convince you that elements which lie in the union of the sets satisfying C1, C2, and so on, Cn contributes 0 to the left-hand side and 0 to the right-hand side. And in this way, our proof of the formula would be completed. Okay, how do we do this? Well, let's pick an element which lies in just one Ci and not in any other guys. So just it belongs to a single, satisfies just one condition and no else, no other else. Well, then it contributes 0 to the left-hand side because it satisfies Ci, and we're only counting those guys which violate all the condition. Now it contributes 1 to n because it lies in the ambient set, and it contributes 1 to n of Ci, but with a minus sign. So its total contribution to the right-hand side would be 1 minus 1, 0. It contributes 0 to the rest of the elements. Okay. Now let's, for example, take an element which lies in the intersection of just two guys, which satisfy just two properties and no more. And I'll be convincing you now that it still contributes 0 to the left-hand side and 0 to the right-hand side. So assume, yeah, maybe I should have, maybe let me write some words of my proof. Assume that an element small s in S lies in S minus those sets in the union of SC1, SC2, and so on, SC. How many did we have? N. Then it counts as 1 in the left-hand side of formula and in the right-hand side. So such elements are okay. Now, so this would be our first step. So step 2, assume that S belongs to S of Ci and no other. So it just satisfies condition Ci and no other. Then it contributes 0 to the left-hand side, and it contributes 1 minus 1, which is again 0 to the right-hand side. So it contributes 1 to n, and it contributes 1 to n of Ci. And to other guys, it contributes 0. So it would be 1 and then minus 1. Now, let me say, assume that S belongs to some intersection, S of Ci intersected with S of Cj, and no other guys. So we'll look at what it contributes again. So S contributes 0 to the left-hand side. Now it contributes what? It contributes 1 to n. It appears twice in S of Ci and S of Cj. So we subtract it twice, -1, -1. So this is Ci, Cj. And now it appears still once in the intersection. So this one comes from Ci intersected with Cj. So the total would be 0 again. So in general, if S belongs to the intersection of some Ci1, Ci2, Cil, and no other guys. Oops, Cil, and no others. So then the count would be as follows. It still contributes 0 to the left-hand side, and now it contributes 1 minus L, which is L choose 1, plus L choose 2, because it appears in that many pairs, minus L choose 3, plus, and so on, plus -1 power L, whatever, 1 again. So this would be alternating sum of all binomial coefficients, i.e. the alternating sum of binomial coefficients. L choose something. But this sum is 0. Why? Because we can think of it as the expansion of 1 minus 1 power L. If we use the binomial formula here, we'll get exactly the same expression. This would be 1 minus L choose 1 plus L choose 2 minus L choose 3 plus da 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 to the end. But the left-hand side is 0. So this whole thing would be 0 as well. So you probably know that the sum of binomial coefficients L choose something from L choose 0 to L choose L is 2 power L. But the alternating sum is 0. So if we take 1 minus L choose 1 plus L choose 2 minus L choose 3, da da da, alternating the signs every time, so we'll get 0. Okay, this observation finishes our proof. So, okay, so that's how we can show that
Question.
Yeah, is it
CIK, is that the condition CI applied on element K in the set S? Because
yeah,
CI is the
yes,
condition.
yes.
So what
So
is CIK?
so this thing means all elements in S satisfying satisfying CI. Mm-hmm. Okay. There is also an alternative way to express my formula, or not my formula, the classical formula, as follows: alternative way to write the formula. Okay. So that's how it's used in the book. So introduce S0 would be n, the number of elements in the total set. S1 would be, we will be adding up, we'll be adding up the sizes of all sets satisfying just a single condition. Yeah. Now S2 would be, we'll be adding the sizes of the set which satisfies two conditions. Now S3 would be the sum of the sizes of the set satisfying three conditions. And so on. Now then, so what we're counting, which is the size of the number of elements which do not satisfy any of these conditions, would be S0 minus S1 plus S2 minus S3 minus minus 1 power n Sn. So you probably recognize this formula from our example in the beginning. Yes, so we had this. So we were taking all elements, then subtracting the sizes of all individual subsets satisfying one separate condition, then putting back sizes of pairwise intersections, and then subtracting triple intersection, putting back four tuple intersections, and so on. Yeah, and this, in this notation, that's exactly this statement. Okay, yeah. Maybe I can give you one exercise to think about. So just to make something more specific. So count the number of the number of positive integers between 1 and 100, not divisible by either 2 or 5. Okay, can you do this? So we have two conditions: numbers which are even or divisible by 2, and numbers which are divisible by 5. And we want to count how many numbers which are odd and not divisible by 5 in other language. So how should we do that? So first, so let us say C1 is an even number. This would be our first condition. And C2 divisible by 5, yes? So how many numbers are even in between 1 and 100? So this you should know.
50, of course.
50, good. How many numbers are there which are divisible by 5?
20.
20, yes. How many numbers which are both even and divisible by 5?
10.
10, good. So the answer which we are looking for would be then 100 minus 50 minus 20 and putting back 10, yes. So this would be 40 total. No? Yes, 40, yes. 110 minus 70. So there are 40 odd numbers which are not divisible by 5. Good, so far so good. Another nice example related to this is the so-called Euler phi function, which was introduced by Leonhard Euler in his study of prime numbers. And it actually satisfies a whole bunch of nice properties, and believe it or not, people still study this, although it was introduced 360 years ago approximately. Okay, and so first of all, the definition. So if n is a positive integer, so phi of n is the number of natural numbers in between 1 and n. The num is the number of m such that, so m, first of all, so m is in between 1 and n, or should be strict, doesn't matter. M is in between 1 and n, and m and n are coprime. They have no common factors. So, for example, phi of 2 is 2. Sorry, phi of 2 is 1. It's just 1. Yes. Now, phi of 3, so is 2. Yes. So 2 and 1 and 2 have no common factors. 1 is always counted in. Maybe I don't. 1 is not. Yeah. So 1 is always gives 1 to this function. Now, what about phi of 4? Help me. So how many numbers in between 1 and 4? 4 again, 4 is not interesting. So in between 1 and 3 is coprime with 4. So 1 we count automatically, 2 is not coprime, and then 3 is coprime. So phi of 4 is 2, yes? Now what about phi of 5?
What was coprime?
Coprime? No common factors, no common divisors, no. Two numbers are called coprime if there is no non-trivial divisor dividing both of them. For example, 2 and 4 is divisible by 2, so 2 is not counted. So here, for example, we have 1, 3 is not there, and 3 here. Here we have 1 and 2 counting in there. So in 5 we have 1, 2, 3, 4. All of them are coprime with if n is a prime number, then the answer is n minus 1, because all numbers up to n minus 1 are coprime with a prime number, of course. So this thing would be 4, yes, as I mentioned. What about phi of 6? So how many numbers are coprime with 6? 1 is always there. 2 is not good. 3 is not good. 4 is not good. 5. So phi of 6 is 2. So do you follow the definition? Okay. Now the result will prove is the following. Theorem which Euler proved himself, of course. The following nice expression. Phi of n is n times the product over all primes dividing n. P is a prime. 1 minus 1 over p. So for example, let us check that phi of 6 is actually 2. Yeah, so what about phi of 6 according to this formula? It should be 6, yes, times 1 minus 1/2, yes, and 1 minus 1/3. These are all primes which are dividing 2. And now we get, which is 6 times 1/2 times 2/3. So this thing cancel out and we're getting 2. Okay, now how can we prove this nice formula? Okay, so let's introduce, okay, so for each prime p, say I, okay, k dividing, let's see, dividing n, so we define the condition ck as all m's smaller or equal than n divisible by pk. So we're looking at which primes divide n, and for each of them we define the condition that if m is divisible by this particular prime pk, then this would be a condition ck. Yeah, now how many numbers are there which satisfy ck? What is, so the cardinality of ck, or so how many numbers in between 1 and n are divisible by pk? That's obviously n divided by pk. And notice that n itself is divisible by pk. So it's pk, 2pk, 3pk, 4pk, and so on until we hit n. So the number of such numbers is n divided by pk. Now, if we look at n, say we are picking a bunch of such primes, f of, say, ci1, ci2, cil, so which in other words is how many numbers are divisible by pi1, pi2, pi3, and so on, pik. But since those are primes, this would be equivalent to how many numbers are divisible by their product, and this would be, of course, this kind of thing. N divided by the product of those primes. Okay, now we can go back. So what is phi of n? Phi of n is the number of positive integers in between 1 and n such they are not divisible by the first prime, the second prime, and so on. Say we had k primes. Maybe not such a good index choice. Well, okay, let me use maybe small r here. So by the formula, which we had before, this would be the alternating sum over I from 0 to R minus 1 power I. And now the cardinality of the correspondence set, which would be the sum over all index sets from 1 to R. The number of elements in this set is I. And now take n, or divided by the product of the primes, is pi1, pi2, pi oh, maybe use j here, j. Now if we expand it, take it to the common denominator, then we'll be getting something like the product of all pi's, all prime divisors, and here we'll get a certain alternating sum, which if we look carefully, or n times this, we look carefully, the numerator here would be exactly the product of pi's minus 1. And in the numerator, in the denominator, we'll have the product of all pi's. Dividing pi minus 1 by pi, we'll be getting exactly the formula which we wanted, to R1 minus 1 over pi. So I was a little bit skippy here, but it's much easier if we work with a particular example. For example, if we take a number which has only 3 prime factors, then it would be much easier to follow the proof, the steps of the proof. The general case is a little bit bombastic to follow, but I think it has a reasonable discussion in the book. Okay, so let us now make a break, some 5 minutes, or maybe a little bit more, and then I'll continue after the break with the second part. Okay, good. I'll stop sharing and stop recording, and we'll have still some stuff to do. Yeah. Okay, so once again, our first result, which is the standard inclusion-exclusion formula, is that if we want to count the number of elements in the union, complement to the union of some bunch of sets, then we do the following. We take the ambience, the number of elements in the ambient space, subtract the number of elements in each individual sets, add the number of elements in all pairwise intersection, subtract the number of elements in all triple intersection, add up all 4 tuple intersections, and so on and so on. Do this alternatingly. And in this way, we can count the number of elements, those which are not in the union of all sets. Now, let's discuss a certain problem, which is a natural generalization of our first problem, generalized inclusion-exclusion. Okay, so let me first give you a motivating example as before. So we have an ambient set. Say we have 3 sets, A, B, C, or say 3 properties, C1, C2, C3. And we want to count how many elements satisfy exactly one property. So in other words, we want to count the shaded area here. So this plus that plus that. So how many elements satisfy exactly one, or belong to exactly one of our regional sets, satisfy exactly one property. So this would be our goal for this hour, plus some, illustrations of this thing. So let's do again a particular example, extending. So we have say we have 100 students totally. So 35 taking combinatorics, say 30 taking some economics, and say now 30 taking programming. Now say there are 9 taking the first 2 courses, there are 10 taking the second and the third, and say there are 11 taking the first and the third, and then there are finally 5 taking all 3 courses. And our question is, how many students take just one course? So that's a question which is illustrated up here. So we have for set A, up here. So that's exactly an illustration to this picture. Okay, so what do we do? So we should count together how many guys are taking the first course, the second and the third, which would be 35 plus 30 plus 30 again. Now I'm saying we should subtract twice the number of students taking at least 2 courses, which is 9, 10, and 11. And we should put back 3 times the number of students taking all 3 courses together. And this will be 95 minus 40 plus 15, which is 70. Okay. Why do we do that? Well, look. So when we add together this set, and this set, and we're only interested in those guys, we have put the pairwise intersection twice in. All pairwise intersections are counted twice as necessary. So we have to remove them, this thing. But when we did that, we have removed too much. We have removed the triple intersection 4 times. And we should just remove it once. So I have to put back 3 times the triple intersection. I'll now formulate the general theorem. Don't quite know if I'll go through the proof, because proof is kind of similar to the one of the first result, but let me at least formulate it. Okay. And it's a generalization of our first result. okay, so denote. Okay, so we're given a finite set I, S, sorry, and properties C1 through Cn. So we denote as before, denote by Ci, the sum of cardinalities of I is a bad, say J. The sum of cardinalities of sets where we're satisfying J conditions, Ci1, Ci2, Cij, over all index sets I1 through Ij. And now, so we denote by EI. So these are all elements in our set satisfying exactly I conditions. So for example, in what I started this hour, we were counting how many students took just one class. So we were interested in this notation, we were interested in E1. How many students satisfy just one condition, where a condition was to take different conditions were to take different classes. Okay, so our first theorem today was how many students do not do anything. So this, in these terms, this would be E0. So how many students do not satisfy any of the conditions. But now we're trying to generalize the previous result and ask how many students, how many elements of our set satisfy just one condition, just two conditions, just three conditions, and so on. We want to get a formula for that. So in the above notation, so EM is equal sum from G equal to M to N, which is our total number of our conditions. Now minus 1 power G minus M times the binomial coefficient G over G minus M times Sj. So in other words, let me write this formula a little bit differently. Maybe it would be easier to swallow it. This would be, that's the same expression, but written more explicitly. Sm minus m plus 1, choose 1, Sm plus 1, minus Sm plus 2, choose 2, Sm plus 2, plus da 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 da, and the last term would be minus 1 over n minus m s n. Okay. Yeah, maybe we should pick some example, maybe try to do some example. Say if we have 4 sets, So if we have, say, 4 sets A, B, C, okay, how should I say? So if we have such a situation, A, B, C, D, and we want to calculate those guys which satisfy exactly 2 properties, but no more. Okay, now E2, so we have M equals 2, N equals 4 in this case. So we have E2 equals S2. S2 are those guys which satisfy at least 2 properties. Minus 3, choose 1, yeah, which is 3. S4. S3, sorry. So S3 are those guys which satisfy at least 3 properties. And finally, plus 4, choose 2, which is 6. S4. S4 is those guys which satisfy all 4 properties in this situation. So S2 minus 3S3 and plus 6S4. Very nice formula. Okay, yeah, we will probably apply this formula to one nice example in a second. And so the result, the proof of the formula is very similar to what we did for the first theorem. So we should look at those guys, for example, which satisfy exactly M properties. Then they contribute 1 to the left-hand side and 1 to the right-hand side. Now we'll assume that we're looking at, and we have to show that those guys which satisfy more than M properties, they contribute 0 to the left-hand side and 0 to the right-hand side. And this again boils out to a very simple formula for the binomial coefficients. Yeah. So for example, if there is a guy which satisfies exactly M+1 property, then it contributes 0 to the left-hand side, and it contributes M+1 times to this thing, and then we should subtract M+1. So it contributes 0 to the right-hand side. Well, if you can look a little bit careful at the proof in the book, so it's again a rather simple combinat identity about binomial coefficients, which shows this fact that elements which satisfy more than M properties can contribute 0 to the right-hand side of the formula. Okay, let's try to illustrate this thing with a particular example. This would be probably nice thing to get some feeling about what we are dealing with. And our example would be as follows. So say we have 5 villages. So we want to, how many ways are there to connect them by a roadmap? So we have some 5 different villages, and what we want to do, we want to build a set of roads such that no village would be isolated. It would be possible using these roads to travel from any village to any other village. Okay, so usually this is reinterpret it in terms of graphs. Oh, sorry, I think I formulated it in the wrong way. So no village, how many by road map, so that no village is isolated. So it's not the same property as you can go from one to another. So it's just the property that every village is connected at least to one other village by road. Sorry, it's not what I said. For example, so this is a good thing, although you cannot go from those two to those three, but each village is connected at least to some other guy, some other village, or this is a good one. So here you can actually go from any village to any other village. So this is a connected graph. So we're looking for, in other words, graphs on 5 labeled vertices with no isolated vertices. So we want to count those. Count graphs on 5 labeled vertices with no isolated vertices. Okay. So we will be looking on the set of all graphs. So we can see the all graphs on 5 labeled vertices, and introduce so a condition C1, C2, C3, C4, C5, which is Ci is the ith vertex is isolated. And we want to what is it that we want? We want to find out how many graphs are there so that none of the vertices is isolated. Yeah. Okay. So first of all, so our ambient set is the set of all graphs on 5 labeled vertices. So S is all graphs on 5 vertices. Vertices have names, so A, B, or whatever. 1, 2, 3, 4, 5. Well, how many graphs are there? So let's count this thing. So this is the solution. Okay, so how many graphs are there totally? Can you count? What do you think? How many graphs are there with 5 vertices? So vertices are labeled, so we have to, so each graph is associated with edges, yes? So how many edges we can have on 5 vertices? So the total number of edges is 5 choose 2, because edge is a pair of vertices. So there are 5 choose 2, 10 edges, in other words. So in a graph is we can either take an edge or just remove an edge. So the number would be 2 power the total number of edges, which is 10, would be 2 power 5, choose 2, 2 power 10, and 2 power 10 is a famous kilobyte, 1024. Okay, now, so how many graphs are there where a vertex C1, the first vertex is isolated? And this is, of course, equal to n of C2, n of C3, and n of C5. So how many graphs are there with one vertex isolated? So that means that we have no edges from this vertex. Yes. So we have 4 remaining vertices. And on 4 vertices, we can have 4 choose 2, 6 different edges. So this would be 2 power 4 choose 2, which is 2 power 6. Now, if we want 2 of our 5 vertices to be isolated, how many graphs do we have then? So we have 2 isolated vertices, we have the remaining group of 3 vertices, and 3 vertices can be connected by at most 3 edges. So this would be 2 power 3, 2 power 3, yeah. Now, if we want 3 vertices to be isolated, Ci, Cj, Ck, then we just have 2 vertices left to be connected by at most 1 edge. So this is just 2. And finally, if we want 4 vertices to be isolated, so there is just the one way to do that. And again, 5 vertices isolated, C1, C2, C3, C4, C5, that's again just one set. No, to put no edges at all.
It's 4 vertices isolated has to coincide with 5 vertices isolated.
Yeah, sure.
That's got to be the same one.
Yeah, that's the same one, absolutely. So now if we want to count all graphs such that every vertex is non-isolated, so this would be kind of application of in fact of our first formula. But we can also count, okay. And so this would be, we have 1 kilobyte graphs altogether. We have to remove, so 320. So let's see, 2 power 6. This is
64.
64, yes. So this is 8. Now I'm just trying to understand why. Yes, 64. Why should be 5 times 1? Yes, should be 5 times 1 times 64. And then it should be plus 6 times 6 over 6 choose 2 times 8. So I'm a little bit confused. So I have an answer here, but I'm just a little bit confused. So this one. Let's see, what is it that I'm doing here? So 1. No. So I have an answer here, but I'm a little bit confused. So the answer is like this, but I have to think why. Minus 20 plus 5 minus 1 should be 368. Why? 768, so y. Yes. Okay, so we have 5 guys like this. So this would be times 5. Yes. So this would be S1. Okay. Yeah. So this is S0 minus S1 plus S2 minus S3 plus S4 minus S5. Okay. Now, yeah, now I think I got it. Yes, I think I got it. Okay. So we have 64 guys which satisfy at least one property. That means that at least one vertex is isolated, but we have 5 such things. So S1 is the union of those things, and this would be the sum of those things. This would be 5 times 64. Now a pairwise thing gives us 8, so S2 would be 5 choose 2 times 8. Now triple thing would be again 5 choose 3 times 2, and now S4 would be just 5 times 1, and S5 would just be 1. Okay, so these numbers come in here. So 320 is this thing. Now this is 10. So 10 times 8 would be this 80 here. So this thing would be this 20. This would be this 5. And finally, this would be this minus 1. Okay. Yeah. I hope I made it somewhat understandable. Apparently not very much, but still. Okay. Now it's the final thing we'll be doing today. A nice small topic in combinatorics, which is called derangement. And it's closely related to our second theorem, which we were discussing. Okay, derangements are certain type of permutations. They appear apparently in many applications. And let us try to enumerate them. Well, first of all, I'll explain what those are. And we'll try to find first a non-closed formula for those, and then we'll try to find a nice asymptotic formula for those. Let me check how this thing is spelled, because I am not sure whether it's spelled with one derangements. Okay, no, good. So that's a good, correct spelling. So first of all, we'll start with the definition. A derangement is a permutation where no entry stands on its place. Well, in other words, an entry y never stands on the ith place. So let's first check. So we can denote, denote by dn the number of derangements on n elements. Or in other words, how many derangements in the symmetric group of length n we have. Okay, so let's first do some example, of course. So if n equals 2, so we have just two permutations, 2, 1, and 1, 2. So D2 would be 1, because 1, 2 is not good, 2, 1 is good. So just 2, 1, yes. So such permutation is good one. So let's take n equals 3. So we have 1, 2, 3, 1, 3, 2. Then we have, let's see, 2, 1, 3. So it should be 6 of them. Yes, 2, 3, 1. Then we have 3, 1, 2, and finally 3, 2, 1. Okay, so which of these permutations are derangements? So this is not good. No, this is not good. This is not good. So here 1 is in, everybody is in its place. Here 1 is in its position. Here 3 is in its position. So this guy is good. So 1 is not in the first place. 2 is not in the second place. 3 is not in the second place, the third place. This guy is also good, yes. So nobody is in its place, and this one is also good. So D3 equals 3, yes. D4, if we look at n equals 4, I'll not be writing down all 24, but believe me that among permutations of 4 elements, there will be 9 which are derangements, which no, not 1, not 2. 1 does not stand in the first place, 2 not in the second place, 3 not in the third place, and so on. Okay, so first of all, the formula which follows from our previous result, which says the following. So dn equals n factorial minus n choose 1 times n minus 1 factorial, then plus n choose 2 n minus 2 factorial, and minus plus da 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 da, and at the end we get n choose n times 0 factorial. 0 factorial by definition is 1. Okay, why it follows from our previous thing? Well, let's see. Okay, so why is it? This would be minus 1 power n, I guess. Why it follows from our previous observations? Well, so the total number of permutations is n factorial, and if we introduce n properties, that the ith property would be that the number I stays in the ith position. So by our exclusion business, we have to remove the sum of cardinalities of CIs. Each of them is n minus 1 factorial, yes, because we are requiring that number I stays on the ith place, and we're not requiring anything else. So we still have n permutations on n minus 1 positions, the n minus 1 factorial those. So So this explains these terms. Now we have to put back the sum of cardinalities of those permutations where two positions are correct. So I stays at the ith place and j stays at the j's place. So there n choose two choices to choose I and j. And for each of them, we have permutations on n minus 2 positions still left. This explains this guy. And so on. We'll have an alternating formula. So if we fix 3 letters I, j, k, so we have n choose 3 possibilities, and each of them will contribute to n minus 3 factorial additional options. Okay, so this explains this formula. In particular, let's apply it to get 9 here. Okay, so d4 would be 4 factorial, yes, minus 4 times 3 factorial plus, let's see, 4 choose 2 times 2 factorial, and finally minus, no, it's not finally, minus 4 choose 3 times 1 factorial and plus 4 over 4 factorial times 0 factorial. Okay, so what do we get here? 4 factorial is 24. 3 factorial is 6 times 4. So we are removing 24. Now here, so this is 6, and choose 2 is 6, so it will get us 12. So this is 4 minus 4 and plus 1. So we'll be getting totally 9, as I suggested. And the last thing for today would be just one last thing, is a nice preposition. It's about the asymptotic behavior of the number of derangements dn. So dn is proportional for large n is close to n factorial divided by e, strangely enough. So more precisely, so this was just the asymptotic formula. We have a bound n factorial divided by e minus dn. Absolute value is at most 1 over n plus 1. So the difference between n factorial divided by e decreases with n, not very quickly, but maybe they are better bounds, but at least we can get a linear bound on the decreasing of the difference. Okay, so again, so how to prove this? We'll look again at our formula for dn. dn equals sum I from 0 to n minus 1 power I, n choose I, n minus I factorial. Yes. So if we factor out n factorial, we'll get n factorial sum I from 0 to n minus 1 power I. And now look, 1 over I factorial. What do we recognize here? So this is a expansion of E inverse. So recall that E, there is a formula for E, which is 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial, da da da. And if we take E inverse, this would be almost the same formula, but with the alternating signs. So what we see here is this expansion for 1 over e truncated to the ith term. So if we look at the difference, take the absolute value of n factorial divided by e minus dn, and this should be equal to n factorial, and here we have the sum of the remaining part of the expansion of E inverse, which is sum I from n plus 1 to infinity minus 1 power I, 1 over I factorial. And we can we can just take two terms in this thing, because this is an alternating series. It's sum of this series, and it's alternate series with alternating sums and quickly decreasing absolute values of its entries. So we can estimate it by just taking two first terms here, which will give us so the first term would be n factorial divided by n plus 1 factorial. It will give us 1 over n plus 1. And the second term would be n factorial divided by n plus 2 factorial, but with a minus sign. So this will give us the following thing. And this difference is exactly 1 over n plus 2. So this proof requires a little bit of analysis. In particular, the basic thing is the knowledge of these formulas for these series expansions for E, and from which it follows the series expansion of E inverse follows easily. But as soon as you know those, and you know this simple fact that if you have a series with alternating terms and decreasing absolute values of these terms, then you can estimate the whole sum by just taking the first one, or you can take a bunch of first terms and estimate the sum of the whole series as the sum of the first piece of your series. Then this formula will follow. Okay, we had quite a few new results and techniques today, but I hope I haven't overwhelmed you. At least I think this portion of the book is fairly nice, and it has a lot of examples, and is fairly well explained. Okay, so I'll finish now, and you have some 20 minutes maybe to relax till the exercise session. Okay, good. And wish you luck.